Okay, ladies and gentlemen, I'm going to do Chapter 9 quiz, problem number 17. Now, as you know, the quizzes are the homework. So this is the homework problems from Chapter 9, problem number 17. Let's take a look here. We got the jet ski accidents. This is some data that they are giving us. It's the number of accidents that people had when using jet skis. And they want you to use an alpha of 0.05. And then the call of the question is, can it be concluded that the average number of accidents per year has increased from one period to the next? So we got this period and then this period. So the way I was thinking about this was, well, this is maybe the 5 years before the year 2000. This is the 5 years after the year 2000, or something of that sort. Or maybe this was before certain regulations went into effect. This is after certain regulations went into effect. But each one of these data points here represents 1 year's worth of accidents. Okay? And we're trying to figure out is there an increase from one period to the next? And if I may be more precise here, if you carefully look at the call of the question, it says, has it increased from one period to the next period? So what it's asking you is the later period greater than the earlier period? Okay, so here's my handwritten solution. As always, I try to follow a certain pattern, as you know, and let's take a look. Okay, I always write down what I'm given first. We have the following data. We have the earlier period. I'm going to just arbitrarily call that data set number 1. These are the data points. N sub 1, that's the number of data points in set number 1, is 5. There's 1, 2, 3, 4, 5 data points. The later period, that's data set number 2. We have these data points, and that's gives me N2 is equal to 5. And I think it's pretty obvious. I wrote this note to myself, but then it became pretty obvious to me that we assume that each of the data points represents the number of accidents in some particular year, and so that's no big deal there. All right, so find. What are we looking for? We're trying to find using alpha is equal to 0.05, so alpha is 5%. We want to test the hypothesis that the average number of accidents, so we're talking about our X bars then, right? The average number of accidents per year has increased from one period to the next. So when it says to the next, I think it means the later period. Okay, so this is my discussion here. My null hypothesis is that mu1 is equal to mu2. So in other words, the mean of the population for the first group, the first period of time, is equal to the mean of the period of the second period of time. I hope I said that right. In any event, it's easier to write it in math than it is to say it. So mu1 is the earlier period. That's our null hypothesis. Our test hypothesis, our research hypothesis, is that the second period is greater than the first period, and that's our claim. So we're comparing the difference, or another way of saying that is we're testing the difference. We're comparing the difference between two means. They're independent samples, and we do not know the population standard deviations. Now, that's because we don't know them because it wasn't given to us. Now, what I want to point out here, give me 1 second, I'm going to go to that in the book. Okay, I did a video on this, a separate video. There's this one section of the book called Hypothesis Testing Summary. Let me see what page that's on, if I could find it real quick. Looks like it's on page 545 of the 10th edition. Okay, so here it is. I strongly urge you to print this out or copy it, have it at your fingertips, because you can go through this. This is a summary of the techniques in Chapter 8 and Chapter 9. You just walk your way through this, and you can easily, I claim, you can easily find exactly what you need if you just do it in a nice organized fashion. So we're comparing the two means. They're independent samples. We do not know the population standard deviation. So what are we going to do here? Okay, Is it this technique? No, because in this technique we're comparing a sample mean with a population mean. So it's not this one. It's not okay. Is it this one? Is it number 2? No, because we're comparing a sample variance or standard deviation of a specific population. Okay, so we're comparing sample to population in 1 and 2. So sample to population, sample to population. So you got to watch that video. Okay, I go into some detail about this. So let's take a look at this next one. Comparison of 2 sample means. Well, that looks a lot better, right? Because as we saw just a moment ago, we are comparing sample means, 2 sample means. Okay. It says here, use the z-test when the population variances are known. Well, we don't know the population variances, so we're not going to use that one. It says use the t-test. It has to be independent samples, which we have. The population variances are unknown, and we have to assume that the sample variances are unequal. Well, that's an easy assumption to make. That's no big deal. An obvious question, however, is, okay, wait a second. You assume the sample variances are unequal. Suppose they are equal. Well, what do we do then? Well, that's no big deal. There's actually a separate formula for that. If you look on page 502, it gives you the formula for the situation where we assume that they are equal. Okay, so in any event, this right here, this 3b tells us what we need to do. This is it. Okay. All right. So I hope you do that. Take my advice on this. I do this every single time. I look through these formulas, step by step to find out what I need to do. Okay. So here we are, back to my handwritten notes. We're going to use the technique of section 9-2. That's the t-test. When I look at this sort of a problem, and I consider the differences of the means. That's what I'm looking at, the differences of the means. I'm sorry, give me 1 second here. Okay, sorry, it's hard to bounce back and forth here. The difference of the means, that's this, right? You've got x bar 1 and x bar 2. What I'm really looking at is what's the delta? Delta is D as in David, D-E-L-T-A. The delta, what's the difference in x1 bar and x2 bar? Okay, that can be considered as a random variable. And I'm comparing that to this random variable, the mu1 take away mu2. Now remember, mu is referring to the population, okay? Well, by hypothesis, our hypothesis is normally going to be that the mu1 is equal to the mu2. So when you take mu1, subtract mu2, what do you get? You get 0. So this part of the formula normally goes to 0. Okay, so that's what I'm saying about here. Is I'm saying the difference of the means is basically a random variable, okay, with a distribution. And as usual, we're going to consider the same format that we typically use, or I use anyway. The test value that we're going to obtain is the observed value, take away the expected value, and that's the expected value if the null hypothesis is true, and all of that is over the standard error. Now, where did I get that? That's right from the book, right from the book. So this formula or this format, the test value is equal to the observed value, take away the expected value, divided by the standard error. This one right here, he mentions this several times. This is on page 502, which just by coincidence, I'll mention, see page 502. That's actually a good place for me to look at this, because this gives you the formula, which we're not going to use. But this is in a situation where, let's see here, right here, when the variances are assumed to be equal. We're assuming that in our problems, we're assuming that they're not equal. If we assume that they are equal, or if you have reason to believe that they are equal, then we use a slightly different formula. Okay, so it's no big deal. They're just formulas. You just plug them into your calculator. Okay, so this right here, this should be very, very familiar to you. You've seen this a dozen times. Okay, I write it a slightly different way, just because it's just a little bit easier for me to get my arms around it. This, formal formula can also be considered this way. It's how surprised are you? And then you have a yardstick on the bottom. The concept here is that on the top, you're looking at the delta, the difference between the observed value compared to what you expected it to be if the null hypothesis is true. And then on the bottom, you have what is I would consider to be some sort of a yardstick. Okay, so how up on top is, boy, I am really surprised. This is really different than what I expected. So how surprised are you? And then on the bottom is some form of a yardstick. That's my test value, my T. Okay, so here's the formula. You can pause the video to stare at that. Look in your book if you need to. Okay, that's the test value. Okay. No, normally the mu1 take away mu2 is 0 because the null hypothesis is that they are equal. Okay, so our null hypothesis is that they're equal, so mu1 take away mu2 is going to be equal to 0. And then this is our research hypothesis. It's also what we would call our claim. Okay. All right, so here's this formula. Not really that bad. Okay, the first step is going to be to find the critical value, also known as CV, the critical value. Okay, this is a one-tailed test because what our research hypothesis is that one of them is greater than the other. Okay, it's greater than. It's not. We're not saying that it's different. We're saying that it's greater than. Okay, the degree of freedom is you take n1 subtract 1 and you take n2 subtract 1 and you're going to use the smaller one. Okay. Well, in this particular case, they're equal, so either one of them is a smaller one. It's no big deal, right? Okay, so find the critical value from table F. Hopefully by now you've done a bazillion of these. You found that you've used the table many times. You find the critical value of a one-tailed test of alpha is equal to 5%, a degree of freedom of 4. That gives me 2.132. Okay. Now, that's from the table. Now, to be more precise, this is the absolute value of the critical value is 2.132 because we are looking at the null hypothesis that mu1 is less than mu2. So what we really need is the critical value of negative 2.132. This is what we need, is this guy over here. Oops. Okay, so this is my critical region. This is my critical value. That's very important. First step, I got to find the critical value. Okay. Now, this next part is the tedious part, and I'm not recommending that you do it by hand. We're going to use a calculator for it. Use a calculator, or in my personal preference, you use a website. I personally use this website, www.calculatorsoup.com, but there's others. You can use whatever you want. So you punch that into your calculator or your website. This is what you come up with. You come up with an X bar of this 909, blah blah blah. Okay, and you come up with these are the inputs into that formula. For data set number 2, here's what you come up with. Again, it's just a matter of cranking it out. No big deal. Okay. Here's my message. Don't be intimidated. They're just numbers. You plug them in. Keep yourself organized. Spread things out. Write it down. Write sentences explaining what you're doing. It's not a big deal. So what I've done up here, I got all the inputs that I needed for this formula. Okay, I just plug it in. Okay, I plug it in, and this is what I come up with. I crank it out. Boom, negative 4.05. Now it's time to draw our cartoon. Our critical value is negative 2 point blah blah blah. Our test value I just calculated is negative 4.05. So am I in the critical region? Yes, I'm in the critical region. The test value is to the left of the critical value. It's over here. Okay, that's in the critical region. So we are so surprised that we reject the null hypothesis. So there is enough evidence to support the claim that accidents have increased. The idea is it's not just due to chance. I mean, maybe it is. Maybe it's due to chance, but it's so unlikely. It's the likelihood of that being due. Got it. The likelihood of that being due to chance is so small that we reject that null hypothesis. Sorry, I was running I'm running out of time here. So I hope that helps. This is a typical type of a problem, kind of a boring problem, but it has it's a metaphor. There's all kinds of other applications. All right, thank you.